You use the you use the convention that when you do the inverse, you use the restricted domains of those functions. So you only go from 0 to 180 when you're doing cosine. Does that make sense?
Yeah.
Okay. All right. So this leads us to something that's pretty useful for us. The sine of the dot product will actually determine what kind of angle is made between the two vectors. Okay, so if we have u dot v, let's look at it like this, which we know is magnitude u, magnitude v, cosine theta. This determines the sine. So it determines whether the dot product is positive, negative, or 0. Okay? So if the cosine of theta is greater than 0, what kind of angle do we have between the two vectors? Cosine's positive, so that's quadrant 1, right? 0 to 90, so what kind of angles are those? Acutes. We did this one already. If the cosine of theta is equal to 0, that's a right angle. And if the cosine of theta is less than 0, that's an obtuse angle. Okay, so these are pretty important, but the most important of all is the fact that when you do the dot product, if u dot v is equal to 0, which is the coincidence that we observed in the previous example, this means that what? The two vectors are perpendicular. I guess it's time to introduce some notation. In the context of vectors, we're going to say orthogonal. If you need to write down a little note that means that they're 90 degrees or perpendicular, then go ahead and do that. In fact, we could clear some of this lingo up. Perpendicular is typically used when talking about planes. So we say perpendicular planes. We say orthogonal vectors. And there's a new one which we'll talk more about in one of the later sections. We say normal. And that's in the context of a vector normal to a plane. But they all essentially mean that we're talking about 90-degree angles. Okay? So perpendicular planes, you guys know what that looks like already. XY plane, YZ plane, XZ plane, those are all perpendicular planes. Orthogonal vectors are just vectors that make a 90-degree angle. A vector being normal to a plane looks something like this. Okay, so that's the context that we'll use it in. Okay. And if you're watching this video, I apologize, but you missed the first half of the lesson. So I'm going to scan in the notes that I gave. Or I guess I could, you know what, I could just do this. You can pause the video, So here's the first part. You may pause it and then write it down, and then ask questions later if you need to. Here are some properties. A little proof of the first one. And let's see. The proof for the other formula of the dot product, which relates the angle between the two vectors, is right here. And this is the example we just did previously, which led us to this whole thing about the sign of the dot product. And now you're caught up. Okay, we'll just do it like that. Now I don't have to scan anything. Woohoo! Okay, assuming this doesn't crash again. Okay, direction angles. These angles are the angles between a vector and the coordinate axes, so x, y, or x, y, and z. So for instance, let's say this is v. This is your usual x and y axis. We'll call this angle with respect to x, positive x, alpha. And the angle between v and positive y we'll call beta. So just knowing these two angles determines the direction of the vector. So the direction of v is determined by the direction angles alpha and beta. Okay, so obviously if I said alpha is 30 and beta is 60, you know exactly which direction v is pointing at. Okay? In 3 dimensions, so this is in 2D. Okay, let's see if I can. So here's x, y, and z. And just to illustrate where this vector is oriented, I'm going to go out a little bit, to the right a little bit, and then up a little bit. And this is v. So I'm starting the vector at the origin, pointing in the first octant where everything is positive. Okay, and it's the same convention. So now the angle between v and x, that's alpha. The angle between v and y, it's kind of hard to do, but that's beta. And then now the angle between v and z, that's going to be gamma. Okay, so we have the same exact idea, but now it's in 3 dimensions. So instead of measuring the angle from v to x, which is alpha, v to y, which is beta, we're also going to measure the angle from v to positive z, and that's going to be called gamma. Okay? So now, to determine the direction angles, so to determine alpha, beta, and gamma, we can use the cosine theta formula, which was u magnitude of that times magnitude of v. Nope, other way around. Sorry about that. U dot v over the magnitude of each. So we're going to use this formula, but make it as easy as possible. So let's start with cosine alpha. So right now I have an arbitrary v vector. And now if I'm looking for the angle between that and the x-axis, what's the easiest vector I can use that's along the x-axis? Well, it would have just an x component. I would be the easiest one, right? I mean, you could use any vector you wanted to. The angle is still going to be the same. Does that make sense? So we're just going to use the unit vector because it'll make the calculations easier. So if I have v dotted with I, then that's going to be divided by the magnitude of v times the magnitude of I, which we can simplify a little bit. V would be v1, v2, v3. What's the unit vector I components? 1, 0, 0. I'm going to leave the magnitude of v as the magnitude of v. What's the magnitude of I? 1. When you take this dot product, the only thing that really is left is v1. So you get v1 over v, the magnitude of v. Okay. Similarly, one of every math teacher's favorite arguments, we can find the other angles. Cosine of beta, we're going to take the magnitude of v dotted with what? Which one? J. So what's the only component that's going to be left on top when you do the dot product? v2, and we're still going to have the magnitude of v in the denominator. And the last cosine angle, cosine gamma, what's going to be the formula for that? Yep, over. Oh, that's not what I meant here. That's just v. There we go. Okay, so cosine alpha equals v1 over the magnitude of the vector. Cosine beta equals v2 over the magnitude of the vector. Cosine gamma equals v3 over the magnitude of the vector. These are called the direction cosines. Where have we seen this type of thing before? v1 over the magnitude of v, v2, unit vectors. Very good. In fact, let's make a special note. The normalized form of any vector v equal to v1, v2, v3. We already have a formula for that. We just say, let's take v and divide the whole thing by the magnitude. Well, if you actually wrote that out, that's exactly v1 over magnitude of v. Oh, I did it again. There. I. We'll write it in this format. v2 over magnitude of v, j, plus v3 over magnitude of v, Okay? And these here are the direction cosines. So whenever you normalize a vector, the components of that unit vector are the direction cosines. Okay? Does that kind of make sense? A theorem which you'll probably do for homework and prove, which I kind of just planted a big seed to help you do that, is that the cosine squared of the direction angles, if you find their sum, maybe you already know. Yeah, I mean, it pretty much did it for you, unofficially, right? Because cosine alpha is this component, that component, that component. This is essentially just finding the magnitude. Okay, and we know that the magnitude of the unit vector is 1. Okay, we'll finish with one problem, and then we'll finish up tomorrow. So here's an example. Let's say we want to find the direction cosines and angles of v equal to 2I plus 3j plus 4k. So find the direction cosines and then an angle in degrees, let's say, to the nearest degree. product is one of two ways that you can multiply vectors together. It actually will make more sense tomorrow too, but essentially the dot product also tells you how big a vector is along the direction of another vector. Okay, so right now all you need to know is that the dot product is simply the components of two vectors multiplied together. Answers, by the way, 68 degrees, 56 degrees, 42 degrees. And then the inverse cosine is obviously, if you have that, you have them.
You know for homework that yellow packet is
I think it's close to the book. What's your name? It's close to the book.
Yeah. So, I don't know, did you get this part down? Yeah. Well, both the video. So that's the definition of the note. Just multiply the components.
I'm kidding, but I'm really going to tell this. So you have this, right? You have that. Then you have to divide everything by this. And then once you get that.
And that happens to be the projection.
Okay, so okay, that makes more sense.
Yeah.
I'm gonna have to do
Thursday? Okay.
Field trip to some tutoring thing.
Okay.
So
Just remind me tomorrow.
Can I take a picture of the notes that we take in class or something?
Yeah.
That doesn't seem to be working.
Yeah, I'll figure it out.
Okay. Do I need to get like your signature or anything?
For a field trip?
Yeah.
I mean, if you have a field trip form, sometimes I just bring them in and I'll sign it, but it should be
Sounds
fine.
good.
I have a quick question.
Give me 1 second so I can just write this up here.
Please not until you are emotionally down.
So you
These are the answers.
like